Now, we know some standard forms, but out of curiosity let us just examine the form of the inversion formula for the Laplace transform. If we have the Laplace transform of a function, how do we find x of t? If you want to go through it by formal means, then we start by recognizing, wait, inversion of the Laplace transform. So, suppose we already know that if you have x t, if you have xs, then it is the Laplace is the continuous time Fourier transform of x t e to the minus sigma t. So, this is what we have. So, we can write then that x t e to the minus sigma t equals the inverse Fourier transform 1 by 2 pi integral minus infinity to infinity x sigma plus j omega e to the power j omega t d omega. This is just the inverse Fourier transform of xs, and as we said, that will be equal to x t e to the minus sigma t, because the Fourier transform of x t e to the minus sigma t was the Laplace transform of x t. Okay. If we have this now, then we just multiply both sides by e to the sigma t, so that we have only x t on the left side, and get x t equals 1 by 2 pi That means, we have to integrate x s over all values of omega, but do so at a place where the Laplace transform exists. That is to say, at a place where x t e to the minus sigma t is absolutely integrable. That is, in other words, within the ROC. So, integration must be carried out from omega equals minus infinity to omega equal to infinity of xs at, on the S plane at a point where x of sigma plus j omega converges. That is the kind of place where we should do this. Now, once we recognize this point, we can make the final changes to bring the expression into proper form. S equals sigma plus j omega. So, ds by d omega equals plus j, or d omega equals ds by j. You have this. Furthermore, we have that S, as we just said, must be chosen. The points over which integration is carried out must be chosen to lie within the ROC. So, we will say x t equals 1 by 2 pi times j, which has come from over here, j has come from over here, integral s equal to sigma minus j infinity to s equal to sigma plus j infinity of x s e to the power minus s t ds. Where sigma is a point in the ROC of xs. If you try to integrate it over a point outside the ROC, obviously it would not converge. So, you have to do it inside the ROC and then it will converge. So, this gives us the expression for the inverse Laplace transform of an arbitrary function xt, of an arbitrary function xs. We can always do this, but as I said that we only deal with a few standard forms. So, what we can instead do is simply to reduce the problem given to us to one of these standard forms and then apply common sense, superposition and one or two other things. So, that is what we will now proceed to do in a couple of examples. The general form of the Laplace transform of a function need not be straightforward, because once you get, even for example in the previous case we had s plus 2 s minus 1, where was that? Well, wherever it was, suppose you have xs equals 1 by s plus 2 plus 1 by s minus 1 or this sigma greater than minus 2, rather minus 1. Sigma greater than plus 1. Suppose we have this. Then what we will see is not a nice broken down expression like this. We will unfortunately be given something like s plus 2 s minus 1, and in the numerator we will have s minus 1 plus s plus 2 equals s plus 1. This is what we will be told is xs, and we will be asked to get the solution. So, the right way of going about it is to first develop a technique or identify a technique that will break up an expression of this form to a form like this, and that, as we know, is done very effectively by partial fractions expansion. There are still some more complications to worry about. Remember that if we really want to invert any of what we shall call the elementary expressions, then we must have the elementary expression such as this, or such as this. We should have the elementary expression along with its own ROC. Only then we know how to invert it. If this problem is not clear, recall that for xs equal to 1 by s plus a, which is an elementary expression, we do not know what is the inverse transform of this. If we are told that sigma is greater than minus a, then we will write xt equals e to the minus at ut. If we are told sigma is less than minus a, then we will have to write xt equals minus e to the minus at ut. So, it matters. It is not sufficient to be able to expand using partial fractions expansion the general form such as this into a sum of individual partial fractions. That is not alone sufficient to solve our problem. We also require to know the ROCs of each individual term. Now, in order to answer this question, let us see that the ROCs have a certain interesting relation with the algebraic expression. Let us look at a couple of examples and this will become clear. Suppose we have xt equals cos omega naught t ut. Suppose it is cos omega naught t ut. We know that this has a Laplace transform expression of s by s squared plus omega naught squared with sigma greater than 0. This is what we have. Now, let us look at the expression for let us look at the way we can factorize this expression. This can be written as s times s plus j omega naught s minus j omega naught. So, on factorization into first order terms, the denominator has become this. In general, it is convenient to factorize into first order terms. We are already aware that for systems described by differential equations, the expression will be in the form of a ratio of polynomials. So, xs will be in the form some bs by as. We make this claim on the basis of our experience with the continuous time Fourier transform. Now, this can easily be buttressed by actually looking at the Laplace transform of a differential equation, but we will do that in a little while. Now, so long as it is in rational polynomial form, then there will always exist a certain factorization k equals 1 to m of s minus zk over pi k equals 1 to n of s minus pk. Now, just as with the Fourier transform, let us see what happens if s takes on values pk or zk. It goes without saying that both pk's and zk's are either real, because the coefficient of the differential equation will be real, or the pk's and zk's will be found in complex conjugate pairs. This is a discussion we have had already in different contexts, and the same arguments hold here. You see, whenever s approaches a pk, xs will approach infinity, because a factor of the denominator is becoming 0. Likewise, whenever s approaches a zk, then xs approaches 0, because the factor in the numerator is going to 0. This is why the zk are called zeros and the pk are called poles of xs. They are called the poles and zeros of xs. Now, these poles and zeros play a very interesting and important role in determining the ROC. This has been a digression from the problem we were discussing over here. So, let us demonstrate the significance of the poles and zeros for this particular problem first. Let us plot the poles and zeros of cos omega naught t ut, which transformed to S by S plus j omega S minus j omega, omega 0 of course. Now on the S plane, where you have sigma on the horizontal axis as I said and j omega on the vertical axis, the roots are minus j omega naught and plus j omega naught. So you have a root over here at omega naught and here at minus omega naught. These are the two poles. If we consider earlier examples such as xt equal to e to the power minus at ut, which had a transform of 1 by s plus a, then for that the Laplace transform, this was sigma, this was j omega. The root of this is already a first order factor, so the root is simply s equal to minus a. So at some place over here minus a, you have a root. So these are the poles. Now consider this expression. Here we found two instances, one where the ROC was sigma greater than minus a and the other where sigma was less than minus a. So minus a served as a boundary in both cases. Minus a serves as a boundary. Sigma equal to minus a serves as a boundary for the ROC in both cases. So for sigma greater than minus a, that is for xt, let me just mark out the boundaries first. This was sigma greater than minus a and corresponded to xt equals e to the minus at ut, or you could have and this was sigma less than minus a corresponding to xt equal to minus e to the minus at u of minus t, all for the same expression 1 by s plus a. Right. So this is what we observe. Now let us look at the cos omega naught t ut example once again. Here the ROC turned out to be this. You have not one pole but two poles over here, but again they are serving as a boundary. Poles generally serve as boundaries. Let us take the other example where the left side is the ROC for this case. Suppose you take xt equals cos omega naught t u of minus t, then it is a function that will expand leftwards. Probably you will have to take minus cos omega naught t u minus t. That is something you can settle by just solving the integration. But for this you would get an expression that is similar to this, but it would have an ROC of sigma less than 0, and you would therefore get this as the ROC. This is for sigma less than 0, this is for sigma greater than 0. Again you see that the places where the poles are, the vertical line containing the poles serves as a boundary. So this reinforces what we have just found over here. Poles serve as boundaries. With this in mind, let us try to get a slightly more refined understanding of what is the problem of finding the inverse Laplace transform given the expression, given the algebraic expression. First, as I said, we will have x s x s as some b of s by a of s. This we will express as a product of first order factors s minus zk by product of s minus pk. This we will do. Then we will plot all these zeros and the poles on the S plane. Zeros are marked a small circle like this and maybe this, and the poles are marked by a cross like this, maybe one more over here, one more over here, and so on. Maybe we can add a couple of zeros as well. So we have these zeros and poles littering the S plane, where this is sigma and this is j omega. So we have these poles and zeros scattered, and we can find their locations by factorizing the original expression of the Laplace transform given to us. Furthermore, we will have the ROC of the entire expression, the ROC of the entire function, ROC of the entire function is given, and it is left to us to decompose the ROC into components and match them against the individual partial fraction parts. So on the one hand, we will expand into partial fractions, expand excess into partial fractions, then express the given overall ROC as an intersection of component ROCs. So that we match up the component ROCs with the partial fraction terms. To invent the component ROCs, we use the fact that the individual poles or conjugate pole pairs poles or conjugate pole pairs of each partial fraction term serve as a boundary for its ROC. For its respective ROC. So, given a particular term, it has only two possibilities, ROC towards the left or ROC towards the right. There are other possibilities in some rare cases, but we will come to them eventually. So, what we have to do is to consider all the possibilities for each term and see which the intersection of which combination of ROCs yields the given overall ROC. This helps us to determine the component ROCs, the appropriate component ROCs. So, the appropriate component ROCs must yield the overall ROC by intersection in the absence of pole 0 cancellation. Fine. In order to get further insight into the behavior of the ROCs and their properties, we shall now investigate some properties of the ROC. A self-evident property almost is something that we have been observing all along, that the ROC or the region of points on S at which XS converges depends only on a value of sigma. That is, it depends upon whether S is greater than some value A or sigma is greater than some value A or less than some value A. It does not depend upon the value of omega. So, the ROC does not depend, this is property number 1, does not depend on omega, only on sigma. This is easy to prove. What we are saying is, if S is in the S naught is in the ROC of x t, it simply means where S naught equals if S naught equal to sigma naught plus j omega naught is in the ROC of x t, it simply means that x t e to the minus sigma naught t is absolutely integrable. And the absolute integrability of x t e to the minus sigma naught t is very obviously not affected by the choice of omega naught, because omega naught does not even appear in this expression. It does not depend on omega naught. The absolute integrability does not depend on omega naught. Does not depend on omega naught. Thus, the upshot of this entire thing is that if sigma naught plus j omega naught is in the ROC, which we write by saying is in R, then sigma naught plus j omega, the set of points sigma naught plus j omega, minus infinity less than omega less than infinity is a subset of R. That means all those other points are also in R. That is one property of the ROC. Another significant property is that since the ROC is the set of points S at which XS converges, and since XS clearly does not converge at S equal to Pk for any k. That means S, the XS does not converge at the poles, at the points of the poles. It follows that no poles can lie within the ROC, as that would violate the definition of ROC. Fine. So, let us consider that point to be clear. No poles must lie within the ROC. In other words, we can clearly see that when we look for the ROC for some function, we should find areas which are not interspersed with poles. Next, if xt has finite support and is absolutely integrable, then its ROC is the entire S plane S. Now, how do we prove this? Xt has finite support and is absolutely integrable. Since it has finite support, let us say that the boundaries of the support are A and B. So, let xt be equal to 0, t less than A, t greater than B. Suppose we have this xt given to us. Then we also know it is absolutely integrable. We know that minus infinity to infinity x t dt, which is just equal to integral a to b mod xt dt is finite. We know this. If this is finite, then all that we are worried about is the absolute integrability of xt e to the minus sigma t. Of xt e to the minus sigma t. Now, here what do we find? We find that we are concerned with whether minus infinity to infinity mod x t e to the minus sigma t dt, we are concerned with whether this is finite. This is what we are concerned with. But mod x t e to the minus sigma t dt, this equals x t mod times mod e to the minus sigma t. The second factor in this product is always non-negative anyway, even without the mod sign, because e to the minus sigma t is always greater than 0. So, this is just equal to mod x t e to the minus sigma t. Fine. And this function, if you look at it and compare it with the area integral of the original function, then you find the following. Well, e to the minus, consider e to the minus sigma t over the interval a b. Given that these are monotone functions, that is, it either increases monotonically or decreases monotonically depending upon the value of sigma, it is clear that the maximum is either e to the minus a t or e to the minus b t. And thus that integral minus infinity to infinity mod x t e to the minus sigma t dt is less than equal to integral minus infinity to infinity mod x t times max e to the minus a t comma e to the power minus b t dt. That is to say that this acts as an upper bound for this integral, given that mod x t is absolutely integrable. So, since mod x t is absolutely integrable over the interval a to b, all these intervals can be replaced by a and b, and we will do that. Integral from a to b and here also integral from a to b. Fine. So, this is what we have. This simply means that for all sigma minus infinity less than sigma less than infinity, sigma plus j omega is inside the ROC. So, this completes the third property. It pertains to signals with finite support. The next property we consider is about the ROC of one-sided signals. A one-sided signal can be either left-sided or right-sided, and you will recall the definition of one-sided signals from previous discussions in this course, that x t is said to be left-sided if there exists t 0 such that x t equals 0 for all t greater than t 0. Likewise, it is right-sided, x t is right-sided if there exists t naught such that x t equals 0 for t less than t naught. That is when you would say it is a right-sided signal. So, for example, causal signals are right-sided. With t naught equal to 0. Anti-causal signals are left-sided. With t naught equal to 0 again, t naught equal to 0. Now, this does not mean that the converse is true. Not all right-sided signals are causal. Example, t naught less than 0, nor are all left-sided signals anti-causal. Example, when t naught is greater than 0. Fine. So, that is just a review of the understanding of what constitutes a left-sided or a right-sided signal. Now, we will go to the actual claim about the ROC. It is claimed about the ROC that if S naught equal to sigma naught plus j omega naught is in the ROC of a left-sided signal x t, then all S 1 equal to sigma 1 plus j omega 1, where sigma 1 is less than sigma naught, will also lie in the ROC of x t. The argument is simple. We are saying that sigma 1 is less than sigma naught, and we already know that x t e to the minus sigma naught t converges, that is absolutely integrable. When e to the minus when x t e to the minus sigma naught t converges, or is integrable, x t e t minus sigma 1 t, which is actually equal to x t times e to the minus sigma naught minus sigma 1 t times e to the minus sigma naught t. Sorry, just a minute. This is equal to this. Fine. Now you see, this is equal to e to the minus sigma naught t multiplied by this term e to the minus sigma 1 minus sigma naught t. Now since sigma 1 is less than sigma naught, sigma 1 minus sigma naught is less than 0, so that e to the minus sigma 1 minus sigma naught t exponentially decreases as t decreases. Hence, integral minus infinity to infinity x t e to the minus sigma 1 t dt is actually less than integral minus infinity to infinity x t e to the minus sigma naught t. This guarantees convergence. So, summarizing, we found that for a left sided signal, x t, if S naught is a point in the ROC, then the ROC extends leftward indefinitely beyond S naught. That is the claim. We will say that the ROC is leftward. Leftward. By analogy and by very similar arguments, but symmetrically different from the present, from what has just been made, we can say that when x t is right sided and x t e to the minus sigma naught t is absolutely integrable, at S naught equal to sigma naught plus j omega naught, then the ROC of x t extends indefinitely to the right. the right of S naught. This is called a rightward ROC. In both the case of the left sided and the right sided signals for which some ROC exists, we have found that the entire ROC becomes a half S plane, half of the S plane to the left of S naught or to the right of S naught, depending upon left sided signal or right sided signal. So, left sided signals have leftward ROCs, right sided signals have rightward ROCs. Finitely supported signals have ROCs everywhere as long as the signal itself is absolutely integrable. Finally, we come to the last possible case when is two sided, that means it is neither left sided nor right sided, it extends for all time, then it may be expressed with respect to some arbitrary T naught as a sum of left and right sided signals. X t equals x L t plus x R t, where x L t equals 0, t less than t naught, and x R t, t greater than t naught, this is left sided function, t greater than t naught, and x R t equal to 0 for t less than t naught. Now, x R t will have an right sided ROC, x L t will have a left sided ROC. If not, and we are not guaranteeing that x L and x R both have ROCs, we are only saying that if x L has an ROC, it will be left sided. RL, it will be a leftward ROC. If XR has an ROC RR, it will be a rightward ROC. This follows from the previous results we have. Now, if both these things are true, then we can say that x t will have an ROC equal to RL intersection RR if that intersection is non-zero. Non-empty is more precise. So, this is what happens with two-sided signals. So, this information helps us to find the ROCs for the individual component terms in a partial fractions expansion. In order to illustrate this whole thing, I propose to work out just one example, though I will skip some of the details, the algebraic details in proceeding through the example. So, let xs be given as minus 7s minus 53 minus 7s minus 53 divided by s cubed plus 5s squared plus 17s minus 123 plus 17s minus 123. Now, that looks like a terrifying expression, and it indeed is. And to be honest with you, I know how to carry out the partial fractions expansion of this straight away, only because I started with the partial fractions expansion and combined the terms to obtain this. So, let me just go backwards through my notes and tell you what this will expand to. Remember that to expand this expression, you will first have to factorize this. You have to factorize this expression, factorize the denominator expression into separate factors. If you do that, it turns out that this equals minus 7s minus 53 as we said divided by s plus 4 whole squared plus 5 squared times s minus 3. This is what it comes out to be, and then we do a partial fractions expansion to get two terms xs equals s plus 4 by s plus 4 whole squared plus 5 squared minus one by s minus 3. This is what you get. Now, from the expressions we have already presented for standard forms, we could invert both these directly. Let us say that we have been told that the ROC of this is greater than 0. Suppose the ROC has been specified as the set of all s equal to sigma plus j omega, where minus 4 is less than sigma is less than 3. Suppose we have been told this. Remember that we now need to associate each term in the partial fractions expansion with its own ROC. Now, we know if we look at the first term that it will be of the form e to the minus 4t cos 5t. It is either minus this multiplied by u minus t, in which case it would be a leftward signal, or it would be this expression. Let me write both of them. It is either this times ut, in which case it is right sided, with r given by sigma greater than minus 4, or it's equal to minus e to the minus 4 t cos 5 t u minus t. In this case it would be left sided, okay, and r would be sigma less than minus 4. These are the two possibilities for the first term. For the second term, which is 1 by s minus 3, we have very clearly that the time function is e to the power 3t ut, with which would be right sided, it would be right. For the second term, the time expression would be e to the minus 3t ut, that is the first possibility, right sided, with r given by r is greater than minus 3t, sigma greater than minus 3t, or we could have e to the minus of e to the minus 3t u of minus t, which would make it left sided, and you would have r given by sigma less than minus 3, sigma less than minus 3. That is what you would get. So, these are the two possibilities for the second term. Now, we can combine these 2 plus 2 possibilities in 4 different ways, but only one of them will yield by intersection the ROC that has actually been specified for the problem, namely this ROC. This ROC is matched by only one of the 4 possibilities. So, what are the 4 possibilities? The first case is to take the first one of this, with the first one of this, right, and if we did that, we would have an ROC that is greater than minus 4, sigma greater than minus 4, and sigma also greater than minus 3. So, we would get a right sided ROC because both functions are right sided. So, we expect a rightward ROC, and that is what happens. So, that is fine. That would be the first case, but that does not agree with the ROC we have been given. Next, you can consider the first possibility of this combined with the second possibility of the second one. If we did this, we have a sum of a right sided function and a left sided function to get a two sided function. But what would its ROC be? We would get an ROC which is bounded by minus 4 on the left side and bounded by minus 3 on the right side. We would get the narrow band between minus 4 and minus 3, and that does agree with the specified ROC over here. That means what we are looking for is the first possibility of the first term combined with the second possibility of the second term, and we have the answer. The answer is e to the minus 4t cos phi t ut minus e to the minus 3t u minus t. E to the minus 4t cos 5 t u t minus e to the minus 3t u minus t. This then is the xt we are looking for. Okay. Other possibilities that we would have got, you can easily describe. The possibility we have already considered was, this is the correct one. The possibility we have just considered before was this one, which was xt equal to e to the minus 4t cos 5t cos 5t ut plus e to the minus 3t ut, which turned out to be not what we wanted, but what we just did now was the case. So, this was, I think, marked with this color, and then there are two more possibilities. Let us just revert to the previous page and take a look. We can take the second possibility of the first term and the second possibility of the second term, in which case we would get sigma less than minus 4, sigma also less than minus 3. This would happen because we have chosen both left sided signals. So, the sum would be left sided and it would have a leftward ROC sigma less than minus 4. This also does not agree with the specified ROC for the overall expression. Finally, we have the fourth possibility, where we take the right sided expression, the second possibility for the first term, which is the left sided expression, minus e to the minus 4t cos 5t u minus t, and combine it with the first possibility of the second expression, e to the minus t 3t ut. Now, this would give again a two sided expression, sigma greater than minus 3 according to the second term, sigma less than minus 4 according to the first term, and this would lead to a null ROC. That means to say that that expression would not have a Laplace transform at all, because the basic idea of the Laplace transform, which is to ensure that even though x t may not be absolutely integrable, x t e to the minus sigma t will at least be absolutely integrable, fails in this case, because for no value of sigma will x t e to the minus sigma t ever be able to converge. So, of the four possibilities, we have discovered the correct possibility, we have ruled out one possibility, we have ruled out the other three possibilities, and in fact found one of them to be not even a possibility. This explanation, this example brings out the various possible cases and how one converges to the correct case. Now, I will just draw a few diagrams for the first couple of examples over here, and you can a couple of examples, possible solutions that we tried to give you an idea of how we combine the ROCs. So, for this case, what we do is we make ROCs for the first term. The ROC for the first term is sigma greater than minus 4, so this is minus 4, and you have an ROC like this going all the way, of course. Then you have the other ROC, which is sigma greater than minus 3, and you have this as the thing. So, when you take the intersection of these two ROCs, you would obviously get an ROC which is also right sided, rightward ROC. Now, for x t as obtained in the second one, which turned out to be the correct answer, we have a rightward ROC for the first term, minus 4 yielding a rightward ROC, and a second term minus 3 having a leftward ROC. If you combine these two together, you would get a narrow ROC like this, a boundary at minus 3, another boundary at minus 4, this is minus 3 and this is minus 4, you would get an ROC that is just this much. And that is borne out by our earlier result, that when you have an ROC which is a narrow band, which is the intersection of a leftward and rightward ROC, it must correspond to a two-sided signal. This indeed is a two-sided signal.